Hello everyone, I'm Mikhail Maslov, an associate professor at the Department of Condensed Matter Physics of National Research Nuclear University MIFI. I wish to tell you about the phenomenon of ferromagnetism. Ferromagnetism is a magnetically ordered state of matter in which atomic magnetic moments are parallel to each other, so that the matter has a spontaneous magnetization. Owing to ferromagnetism, some materials, such as iron, can be attracted by magnets, or become the permanent magnets themselves. The phenomenon of ferromagnetism plays an important role in modern technologies. It is a physical basis for the creation of a variety of electrical and electronic devices, such as transformers, electromagnets, magnetic storage devices, hard drives, spintronic devices, and so on. In this course, we shall try to understand the microscopic origin of ferromagnetism, to learn about its experimental appearing, and to build a quantum mechanical theory of ferromagnetism. First, let us give a definition of phase transition. A phase transition is the transformation of a thermodynamic system from one phase or state of matter to another one. During a phase transition, certain properties change as a result of the change of some external conditions, such as temperature, pressure, or others. Examples of phase transitions include the transitions between the solid, liquid, and gaseous phases of a single component, the transition between the ferromagnetic and paramagnetic phases of magnetic materials at the Curie temperature, changes in the crystallographic structure, such as between ferrite and austenite of iron, order-disorder transitions, such as in alpha titanium aluminides, the emergence of superconductivity in certain materials and ceramics when cooled below a critical temperature, quantum condensation of Masonic fluids, Bose-Einstein condensation, and so on. In the modern classification scheme, phase transitions are divided into two broad categories: the first-order phase transitions and the second-order phase transitions. What is the principal difference between them? Let us imagine that we have two phases, phase A, white square, and phase B, blue square. We can implement a phase transition between phases A and B in two different ways. We can paint the white square applying the drops of the blue ink in different parts of the square. This is the analogy of the first-order phase transition. The first-order phase transition begins with the formation of small pieces, nuclei of the new phase. For example, pieces of ice in water. Thus, the two phases can so exist. First-order transitions are also associated with mixed phase regimes, in which some parts of the system have completed the transition, and the others have not. Familiar examples are the mentioned above melting of ice or the boiling of water. However, we can paint the white square another way. We can spread the drop across the whole square, so the color of the square will change from white to pale blue, more blue, and so on. This is the analogy of the second-order phase transition. New phase appears immediately in the whole sample. The properties of this phase qualitatively differ from the previous state. Examples of second-order phase transitions are the ferromagnetic transition, superconducting transition, and the superfluid transition. Thus, ferromagnetism refers to the second-order phase transitions. Phase transitions occur when some thermodynamic parameter, temperature, pressure, volume, and so on, changes. Ferromagnetic phase transitions occur when the temperature changes. Thus, below we shall study temperature-induced phase transition. The temperature at which phase transition occurs is called the critical temperature. It is denoted in general case T sub C. However, for specific phase transitions, the special notation can be used. How to determine the phase A or B in which the system is located? Let us recall the thermodynamics. It is well known that if the system is heat insulated, it is located in the phase with the minimum internal energy E. However, in the experiment, the temperature is usually fixed and the system is not thermal insulated. In these conditions, the phase with the minimum Helmholtz free energy F is realized. So, if the temperature dependencies F sub A and F sub B are known, we can find in what phase the system is located. If Fa of t is less than Fb of t, then the phase A is realized, and vice versa. The criterion on the critical temperature is the equality of free energies F sub A and F sub B. There are two main competitive factors influencing on phase transition. The first factor is the interparticle interaction. It defines the internal energy E. And the second factor is statistics. In other words, the factor of large amount of particles in the system. It defines the entropy S. Thus, the smaller the internal energy E and the larger the entropy S, the lower Helmholtz free energy F. It is well known that the entropy is the degree of disorder. The chaotically the system state, the larger entropy. On the other hand, internal energy tends to its minimum if the system is ordering. So, at high temperatures, the main term is minus Ts. Thus, for the minimum free energy, the large entropy or large disorder is required. However, at temperature tends to zero, the free energy tends to internal energy, while the entropy tends to zero. Therefore, at some temperature, these two factors, energies of ordering and disordering, are equal. This temperature is the temperature of phase transition, or critical temperature. Let us imagine that we have some ordered, for example crystal, and disordered phases. In this case, the internal energy of the ordered phase is less than the internal energy of the disordered phase, and the entropy of the ordered phase is less than the entropy of the disordered phase. From the criterion on the critical temperature, we can obtain the expression for it. Note that in fact everything is much more complicated, because both internal energy and entropy depend on temperature. Phase transitions can appear on the experiment in different ways. For example, the water turns to ice when cooled. Resistance of superconductor is equal to zero below the critical temperature. Magnetization of ferromagnetic material is not equal to zero in the absence of magnetic field below the Curie temperature, and so on. Well, let us summarize the learned facts at the end of the first lesson. So, there are two types of phase transitions, the first order phase transition and the second order phase transition. Ferromagnetic phase transition belongs to the second order phase transitions. Ferromagnetic phase arises below the critical temperature, that is called Curie temperature. In ferromagnetic materials, the magnetic moments of the atoms are parallel to each other. In other words, they are all pointing in the same direction, and magnetization of ferromagnetic material is not equal to zero in the absence of magnetic field below the Curie temperature.